Look at raw data fresh out of an extraction, and it rarely makes sense. You have dozens of variables pulling in different directions, and you need to find the underlying patterns hiding inside that chaos. That is where we run into a common trap. We assume that simply extracting the factors gives us the answer, but extraction just pulls the raw components out. Factor rotation is what we do next to actually make those components readable to a human. The entire point of rotating your data is to achieve a mathematical state known as simple structure. This visual shows what that looks like. Simple structure happens when specific variables load strongly onto specific factors, grouping into distinct clusters. Ideally, every variable is driven by one main factor, and every factor drives at least 3 distinct variables. Notice how the dots don't move relative to one another. Rotation does not alter the actual correlation between your variables. It simply shifts the coordinate axes to align with the clusters, giving us a clearer vantage point to read the data. Without running a rotation to find that simple structure, the underlying meaning of your dataset remains tangled up in the math, completely useless for making decisions. But deciding to rotate your data triggers a mandatory choice. You have to tell your software exactly how to rotate those axes. You have 2 main paths, orthogonal or oblique. This chart highlights an orthogonal rotation. The method forces the new axes to remain perfectly independent. They lock into a rigid perpendicular crosshair, holding exactly at 90 degrees. An oblique rotation removes that restriction. The axes are allowed to tilt, bend, and correlate with one another, adjusting however they need to pass directly through the actual data clusters. This decision effectively sets the rules for how your factors are allowed to behave. Choosing one over the other determines whether you treat your variables as isolated islands or as parts of a connected system. The path you take dictates whether you prioritize absolute statistical simplicity or map the messy, theoretical reality of the exact field you are studying. Let's look at orthogonal rotation first, using popular methods like Varimax. The defining input rule here is strict. Factors must be completely uncorrelated. They cannot overlap. Because the factors are isolated, the output is clean. You get a single, straightforward loading matrix where each row and column is distinct. It also preserves variable communalities perfectly. The total variance explained by the factors lines up exactly as simple row sums of squares. The benefit is obvious. It is statistically simple. You can read the factors one by one. If you have a clean dataset, or if you are just learning factor analysis, this feels like a practical tool. But the math requires a rigid assumption, complete independence. Think about the traits you are actually measuring. If those real-world variables interact naturally, forcing an orthogonal rotation intentionally blinds your model to reality. You are telling the software to ignore how things actually behave. Orthogonal rotation is effective for truly independent phenomena, but it becomes a liability if you use it to force independence onto traits that naturally rely on each other. In the real world, phenomena overlap. They feed into each other, creating complex, intertwined patterns that cannot be neatly separated into independent boxes. Oblique rotations, like Promax or Oblimin, are built specifically for this overlap.
They are the standard for fields like the social sciences, where traits naturally correlate. Instead of forcing a right angle, oblique methods allow the axes to lose their strict independence. They tilt to find a truer, simple structure based on where the data actually lives. This maps reality accurately. In psychology, for example, latent traits like anxiety and depression often move together. A rotation method has to acknowledge that relationship to be valid. The trade-off for this accuracy is analytical complexity. Because the factors are allowed to correlate, their variances now superimpose. You have shared, intersecting data pulling from multiple directions at once. An oblique rotation accurately captures real-world complexity, but you lose the luxury of simple one-by-one analysis. You have to untangle those overlapping factor variances to figure out what is actually driving your variables. When you execute an oblique rotation, you don't get a single clean grid. You are left with 2 distinct matrices. You get 2 outputs. On the right, the structure matrix maps general correlations, including all that overlapping variance. On the left, the pattern matrix contains regressional weights, the numbers showing how factors predict variables. The rule: rely on the pattern matrix for your primary interpretation. The pattern matrix filters out the noise. It isolates the individual variables, stripping away the overlapping correlations so you can actually evaluate each one. Mastering the pattern matrix justifies the heavier workload. It cuts through the correlation and reveals the unique, uncontaminated investment of every single factor. You do not have to guess blindly whether your dataset needs an orthogonal or oblique rotation before you begin. Here is the definitive workflow. Always run an oblique rotation first. Use it specifically as a diagnostic baseline. Once you run it, immediately check the resulting factor correlation matrix. If that matrix shows only weak correlations, you have empirical proof that your factors operate independently. You can safely switch to an orthogonal rotation. But if the factors are highly correlated, the data is proving that the traits overlap naturally. You must stay with the oblique rotation and interpret the pattern matrix. By letting the initial data tell you how it behaves, you replace arbitrary guesswork with a rigorous, scientifically valid diagnostic process. If you are working in the hard sciences, your variables often look like this mechanical sorting process, precise, isolated, and highly independent. If you fall into that category, your diagnostic check will likely send you down the orthogonal path. You can enjoy the simplified, single matrix interpretation with a clear conscience. But if you are a social scientist or a survey developer, your factors will overlap. If you try to force a orthogonal rotation on psychological traits, you risk breaking the structural integrity of your own inventory. There is one final fallback. If you stay oblique, but the factors remain confusingly highly correlated, you might be overcomplicating the model. Consider extracting fewer factors rather than forcing the data into a structure it doesn't fit. Rotation provides the clarity needed to interpret the extracted components. By selecting the right method, you align the mathematical results with the actual nature of the variables you're studying.